Oxidation-reduction reactions. Oxidation-reduction reactions involve electrons being transferred. So one substance donates electrons to the other, which accepts the electrons. We often abbreviate this and call them redox reactions because oxidation reduction just gets really long. Of course, this wasn't around when I was in school, but redox looks like red box, kind of, doesn't it? I just take out the B, but it's not nearly so fun as red box. Okay. A lot of redox reactions involve something reacting with oxygen. So here's some examples of redox reactions. Iron rusting. Iron reacting with oxygen to form iron oxide is a redox reaction. Octane burning. That's reacting with oxygen, right? We looked at this reaction already. That's a redox reaction. Hydrogen and oxygen reacting together to form water. It's a redox reaction. Hydrogen and oxygen make a very explosive mixture. Here's a balloon, and you just know this is going to be trouble, right? Here's a candle. Here's a balloon, and it has oxygen and hydrogen gases mixed together. You give it a little bit of a spark, and it does that. It makes a really loud noise and lifts the ceiling tiles in a big auditorium. It's really cool. And then you think maybe you made the balloon a little too big. We don't have gases, or I'd do it for you, but we don't have gases. But what we have here is now a molecule of water. And so something has changed. And it's an oxidation-reduction reaction. Another one, we can have redox without combustion, without oxygen being involved. We see that most often when we have a metal reacting with a nonmetal. Sodium metal and chlorine gas react to form sodium chloride salt. So here this greenish gas, greenish yellowish gas is chlorine gas. And in this little, there's a name for that guy. I forget what his name is. This little bowl here on a stick. We have some sodium. And these will react to form sodium chloride. It's a little more obvious for this type of reaction that electron transfer has occurred. Because sodium chloride is an ionic compound, right? We've got sodium ions, and we have chloride ions. And over here we had a sodium atom. How does a sodium atom become a sodium ion? It loses an electron. Where did the electron go? To the chlorine. So there was a transfer of electrons. The sodium atom transferred an electron to the chlorine atom, and they both became ions and became a compound. And that's the sort of thing that happens in a redox reaction. So here we have sodium reacting with oxygen to form sodium oxide. This is an ionic compound. Here's sodium reacting with chlorine to form sodium chloride. A metal and a nonmetal. Those are going to be redox reactions. Here we're looking at the ions that form. We've got atoms of sodium, molecules of oxygen, forming ions of sodium and ions of oxygen. And that's because of a transfer of electrons. Electrons, you can't just lose electrons like you lose socks in the house, right? Like, seriously, you search the entire house and the socks are just not there anymore. How does that even happen? You would think that you could do that with electrons because they're so incredibly small, but you can't. You can't lose them. You can give them to another atom or ion, but they can't just be out by themselves. And so if one atom loses electrons, another must accept them. So this is how we remember what's going on here. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So if you gain an electron, you've been reduced. If you lose an electron, that's oxidation. So when we look at this reaction between sodium and chlorine, we see that sodium went from having 0 charge to having a +1 charge. That means he lost an electron. Oil, right? OIL. Oxidation is lost. So the sodium losing an electron is an oxidation. If there's an oxidation, there has to be a reduction. The chlorine had no charge. There's 2 chlorines in here. Each of them gained 1 electron, and then we got 2 chloride ions. And so the chlorine gained electrons, that's reduction. Okay? Oxidation is loss of electrons, reduction is gain of electrons. In an ionic compound, we have a complete transfer of electrons. But you can have oxidation reduction without forming an ionic compound. You can have a partial transfer. If we look at the reaction between hydrogen gas and chlorine gas to form hydrogen chloride. Here we have a hydrogen molecule, 2 hydrogen atoms. They are sharing their pair of electrons equally because each of these atoms has the same electronegativity, the same attraction for the electrons. Here's chlorine. 2 chlorine atoms, covalent bond, sharing a pair of electrons. They are each sharing them equally. But when you rearrange all of this and put a hydrogen with the chlorine's more electronegative and he hogs the electrons. And so now the chlorine end of this molecule is a little bit negative and the hydrogen end is a little bit positive. It hasn't gone so far as to transfer the electrons, but it's kind of partially moved over there. We have an increase of electron density for chlorine. Like it gained electrons. It just didn't gain a whole electron. It gained part of an electron. You could think of it that way. An increase in electron density would be reduction. Losing electron density, decreasing, would be oxidation. Does that make sense? It's easy to look at the metals and nonmetals because they form the ions and say, oh yeah, that's an oxidation-reduction reaction. When we're looking at 2 nonmetals reacting with each other, it's harder to tell. And so we have this little made-up thing that we use to help us identify things like that, and it's called oxidation state or oxidation number. Okay, oxidation state, oxidation number means the same thing. So we assign a number to the elements so that we can track where the electrons went before and after the chemical reaction. And we can see, well, if this oxidation number went up or it went down, then we can tell which one was oxidized and which one was reduced. This is really important here. Oxidation states are not ion charges. Oxidation states are not ion charges. They are imaginary charges assigned based on a set of rules. We made this up, okay? There is no evidence or anything. This is just a little trick we made up to help us identify these things. Ion charges are real and measurable. Oxidation states are imaginary. They're like the imaginary friend that helped you through some traumatic experience at school. You know, you had your imaginary friend with you, right? And it was good. But was the imaginary friend really there? Oh, it's just in your mind. Oxidation states are just in our minds. So, rules for assigning oxidation states. These rules are given in order of priority. So, you take care of rule number 1 first, and then 2, and then 3, etc. So the first rule is that free elements have an oxidation state of 0. So sodium, the metal, oxidation state 0. Chlorine, as a free element, is Cl2. That has 0 oxidation number. These are the elements. They're starting at 0. Okay? Monatomic ions have an oxidation state equal to their charge. In sodium chloride, it's a little bit confusing, but here we're looking at this ionic compound, and that has 2 ions in it, 2 monatomic ions, sodium plus and chloride minus. This ion has a charge of +1. It has an oxidation state of +1. And the chloride has an oxidation state of -1. So sometimes the oxidation state is the same number as the ionic charge, but that does not mean that all the oxidation numbers are ionic charges. They're not. The sum of the oxidation states of all the atoms in a compound is 0. So compounds are neutral in charge. They are also neutral in terms of oxidation state. So in a compound such as NaCl, sodium has an oxidation state of +1, chloride is -1. We add those two together and we come up with 0. So all the oxidation states of the atoms have to add up to 0 for a compound. For a neutral molecule, it's 0. For a polyatomic ion, the sum of the oxidation states is going to equal the charge on the ion. So if we look at nitrate ion, oxygen is going to have an oxidation state of -2. Nitrogen is +5, and we take 5 plus 3 -2s, and that adds up to a -1 charge, so a -1 oxidation number. We don't know that yet. We'll get to that. It does have to do with the group. Just overlook that for now. I know it's not the best. So what I'm saying is, I'm just telling you this, and showing you that, yes, they add up to be equal to the charge. And we'll see why they are this and this in a minute. In their compounds, metals are going to have positive oxidation states. The group 1 metals always have an oxidation state of +1. Group 2 always have an oxidation of +2, which makes sense because that's the charge that their ions have, right? And we said it's the bouncing calculator. Is it okay? Yeah, they're much sturdier than phones, aren't they? Thank goodness. The oxidation state is equal to the charge on a monatomic ion, and so this is kind of a repetitive rule there. The nonmetals is where things get a little more complicated. So this is a table that is very useful. What's important to remember is that entries higher on the table take priority. So here's fluorine. Fluorine's going to have a -1 oxidation state. And that, I keep looking at the back wall, the periodic table's over here. That corresponds with the charge that that element likes to have, right? And hydrogen has a +1 oxidation state, which is the charge that it likes to have. Oxygen is -2. The other group 7As are -1. Group 6A is -3. Group 5A is -3. Okay? You can have fractional oxidation states. Awesome, right? And when we write an oxidation state, we write the sign before the number. An ionic charge, we write the sign after the number. And we do that on purpose to try to make them look a little bit different. So let's go back to this one and look at that nitrate ion that was bothering us, right? NO3 minus. So as we go down the rules, The first rule that we come to that applies to this is that the oxidation states of these atoms have to add up to -1. And we keep going down the rules, and we get to rule number 5. It says that nonmetals have these oxidation states, but you go in order from top to bottom. So going from top to bottom, the first one we come to that's in this compound is oxygen. So oxygen gets to be -2. So the oxygen has a -2 oxidation number. If we keep going down, nitrogen is in group 5A. We would expect that it has a -3 oxidation state. But if it had an oxidation state of -3 and oxygen was -2, could the charges possibly add up to -1? No. So oxygen gets to have what he wants, and nitrogen has to suck it up and do something else. Okay, so he's going to have to do something uncomfortable so that oxygen can have -2. We have 3 oxygens here. 3 times -2. And we've got the unknown oxidation number of nitrogen. Let's call it X. And all of this has to add up to -1. So we have X minus 6 equals -1. What's X? +5. So the nitrogen has an oxidation number of +5. That's why. Okay? Does nitrogen have a charge of +5 in that ion? No. No, this is just our way of keeping track of something so that we can predict whether oxidation or reduction has occurred between different compounds in different reactions. So let's do some examples. Determine the oxidation number of each element in these species. So zinc chloride. Well, we really need the formulas. What kind of a compound is zinc chloride? Molecular, acid, or ionic? Ionic, because it's got a metal and a nonmetal. So zinc, when we do ionic compounds, we need to look at the charges of the ions. What charge does zinc ion have? +2. Because it's zinc, it's groups 1, 2, 3, zinc, and silver. We go aluminum, zinc, silver, 3, 2, 1. So zinc is 2+, and chloride is -1. And so they form this compound ZnCl2, right? There's the formula. How do we determine the oxidation states of these monatomic ions in a compound? It's just equal to their charges, right? So zinc will be +2, and chloride will be -1. And the charges add up to 0, which is the charge on the overall compound. Sulfur trioxide. What kind of compound? Molecular. 2 nonmetals, sulfur and oxygen, and that tri is a dead giveaway, molecular compound. So this is SO3, right? So this dumps us to rule 5, where we look at the nonmetals as fluorine, hydrogen, oxygen are getting their way. Oxygen wants to be -2, so oxygen gets to be -2 because fluorine and hydrogen aren't around. And this will determine the oxidation state of the sulfur, because they all have to add up to 0. So this is a similar situation. We have 3 -2s, and then X is going to be the oxidation number of sulfur, and all of this has to add up to what? 0. There's no charge on this compound. This is a neutral compound, so all the oxidation states add up to 0. So the X must be +6. So oxygen's -2, sulfur is plus 6. Is it starting to make some sense? Nitric acid. What is the formula for nitric acid? HNO3. This is an oxyacid because it doesn't start with hydro. Nitric, Rick ate him, comes from nitrate. Nitrate is NO3 minus, so we have one H plus on there to make it an acid. So here we have 3 nonmetals. We're going to look at that table from Rule 5. Fluorine was first, hydrogen was second. What does hydrogen like to be? Plus 1. Next is oxygen. Oxygen gets to be minus 2 because nitrogen is here to make up for everything else. So we've got 1 hydrogen, and we've got 3 oxygens, and we have the nitrogen, X, and these are going to add up to what? 0. So this is going to be minus 6, and this is a 1, so that's minus 5. So the X is going to be plus 5. So the nitrogen is going to be an oxidation state of plus 5. Any questions? How about dichromate ion? Cr2O7 2 minus. Well, that looks like a mess, doesn't it? Chromium is not in group 1, 2, or 3. We cannot predict what its charge would be, and it's not by itself here. So we're going to use minus 2 for the oxygen and figure out what the chromium is. So the oxygen gets to be minus 2. So we have 7 times minus 2. And now we've got plus 2x. There are 2 chromiums. We want the oxidation state of just 1. So we have 2 chromiums times the oxidation state on each of them, and this adds up to what? Negative 2. Okay, so this is minus 9 plus 2x equals minus 2. So I put the 9 on the other side, and I get when I add 9 to the other side, I get plus 7, right? Yeah. Yeah. But 7 plus 2 is 9. I'm like, where did I get that? Oh my. Just keeping you on your toes. I was wondering if we were going to end up with a fractional oxidation state, and that was really bothering me. So I add 14 to the other side, and I get 2x equals 12, right? Then x must equal plus 6. So chromium gets to be plus 6. Any questions? This reminds me of some of the video games that my kids play. They're like, kind of adventuring games, and then there's these little mini games inside of it. And it's like Chem 1A is this adventure game, and then we're playing these little mini games. And nomenclature was one of them, and oxidation states are another one. Drawing Lewis structures. I didn't say they had to be fun, it's just there. We can use oxidation states to identify if we have a redox reaction. So oxidation, we said, was loss of electrons. If you're losing electrons, the oxidation number becomes more positive, just like the charges on ions, right? So oxidation is an increase in the oxidation state. Reduction is a decrease in the oxidation state. So if we look at the reaction between carbon and sulfur to form carbon disulfide, without oxidation states, it's really hard to tell what's going on there because we have two nonmetals. How do we say which one's positive, which one's negative, and how much? We can't. But the oxidation numbers help us out. So here we have carbon. This is the element. It has an oxidation state of 0. Here's sulfur, the element. Oxidation state is 0. In this compound, we go down that table, fluorine, hydrogen, oxygen, and then I think it went group 7, group 6. That would be sulfur. Sulfur gets to be -2. If sulfur's -2 and there's 2 of them, then the carbon must be +4. Now we can look and see what happened to carbon's oxidation state. It went from 0 to +4. That is similar to going from 0 to +4 charge. How do you go to a +4 charge? By losing 4 electrons. Oxidation is loss of electrons. The carbon here is being oxidized. The sulfur is being reduced. If one thing is oxidized, something else has to be reduced. It always happens in pairs. Any questions?
So we look at, so when we're figuring out the rule.
Right.
Carbon, just look at it on its own first on the reactant side, look at the sulfur on its own, and then on the product side, look at the product together, and then go back.
This is a compound, and so we use that table, which gives us an order to look in. Carbon didn't even make the table, by the way. So sulfur gets assigned a number based on the table, and then carbon has to suck it up and just take what's left so that the oxidation states add up to 0 for the compound, which has no charge. These are elements by themselves, and so they're zeros. And after we do all of that, then we look, okay, carbon. Carbon was a 0, and now it's a +4. Its oxidation state has increased. That's equivalent to losing electrons, which is oxidation. They have to occur simultaneously, oxidation and reduction. And here we come to an unfortunate part. This is going to be confusing. So one thing is oxidized and the other thing is reduced. The reactant that reduces an element in another reactant is called the reducing agent. The reducing agent gets oxidized. The oxidizing agent causes oxidation in something else. The oxidizing agent gets reduced. Isn't that fabulous? I know, why? Okay, so let's think about it. What does a Hollywood agent do? Do they act in movies? No. They arrange for other people to act in movies. An oxidizing agent arranges for something else to be oxidized. Yeah? A reducing agent arranges for something else to be reduced. He doesn't get reduced. If something else is getting reduced, then he is getting oxidized. Does that help at all? Well, some of you liked it. I mean, that's the best I've got. It's confusing. It's confusing. Okay. Use oxidation states to decide whether each of the following is a redox reaction. Well, that first one, do we even need oxidation states to decide that? No. We have a metal reacting with a nonmetal to form an ionic compound. These are forming ions. They are actually losing and gaining electrons. That is definitely a redox reaction. But it says use oxidation states. Okay, so sodium has what oxidation state? It's an element. Zero. You're just jumping the gun. You were looking at the other sodium. How about this chlorine? Zero. How about sodium in the ionic compound? Troy? +1? And the chloride? -1. Has it been a redox reaction? Have the oxidation states changed? Yes. Okay, so let's just practice with the agent business. Sodium. Wait, that's not what I meant to do. What is happening to sodium? Sodium's going 0 to +1. That would happen by gaining or losing electrons. Losing electrons. Oxidation is losing electrons. So the sodium is oxidized. The other thing is reduced. Who's the reducing agent? The sodium. The sodium is the reducing agent because the other guy is being reduced. He's not starring in the movie. Chlorine's starring in the movie. Sodium is the agent that allows him to star in the movie. Let's look at this one. Here we have an ionic compound reacting with a molecular compound to form a different ionic compound. We need oxidation states here. So, in calcium oxide, what's the oxidation state of calcium? It's its charge, +2. And oxygen? -2. Okay, carbon dioxide. Who do we have to look at first? The oxygen. So the oxygen is going to be -2. There's 2 of them. So the carbon has to be +4. And now we go over here to the calcium carbonate. This is a monatomic ion still, isn't it? But this is a polyatomic ion. This monatomic ion is still going to be +2. Here's oxygen and carbon. Who do we give the favorite number to? The oxygen. So oxygen gets to be -2. So then we have to figure out what's carbon. There are 3 of these guys, right? So there's 3 -2s. And then there's that carbon that we don't know. We'll call him X. And then we've got the calcium. And this is a compound, so these are all adding up to what? 0. So this is -6, and +2 would be -4, right? So X -4 equals 0. What's X? 4. So the carbon is +4. Is this a redox reaction? No. Everybody kept the same number. No electrons were transferred. It is a reaction, but it's not a redox reaction. See how that works? Yeah. It's going to take some practice, huh? Okay, let's do this one down here. Potassium nitrate. So here we have a monatomic ion and a polyatomic ion. So the monatomic ion gets to have its charge as its oxidation state. What's the charge on potassium ion? +1. And then nitrate, if you want to think of nitrate as an ion and add its stuff up to -1, that's fine. I think it's easier to just look at the whole thing. It adds up to 0. It comes out the same. So nitrogen and oxygen, who has preference in that table? Oxygen. Oxygen gets to be -2. So we have 3 -2s, and we have X for oxygen, X for nitrogen, and we have 1 for the potassium. So this is 1 plus X minus 6 has to equal 0. What's X? 5. So the nitrogen, I'm going to write it above because I didn't leave enough space. The nitrogen's +5. Everybody okay with that? K2O. How do we assign oxidation states for this guy? +1 and -2. This is an ionic compound, monatomic ions, the oxidation state is the same as their ionic charge. So they're pretty easy. Nitrogen, 0, that's an element. Oxygen, 0, it's an element. Is this a redox reaction? Yes. So that's what the question asks. But let's look at this and see what's going on. Is anything happening to potassium? Is it being oxidized or reduced? No, its oxidation state is staying the same. How about oxygen? What's happening to oxygen? Well, one of them stayed the same, but some of them went to 0. -2 to 0. Do you do that by gaining electrons or losing electrons? Losing electrons is oxidation. So the oxygen was oxidized, right? And one of them, nothing happened to. And then the nitrogen went from +5 to 0. It's being reduced. The nice thing about looking at the oxidation numbers is when the number goes down from +5 to 0, going down is reducing, right? Any questions? Who's the oxidizing agent? The oxidizing agent gets reduced, it's nitrogen. This is, I'm guessing, new for everybody because we don't do this in 3A. And I bet you didn't do it in high school either.